Alright, so in this video I'm going to demonstrate some of the differences between working with joints and, well, basically any other type of geometry or control. So I'm going to turn this hierarchy of boxes into dynamic controls. And then we'll get this. And then I'm going to increase the stiffness on all of these boxes. I'm going to add 0 to the end. And we'll get something like that, which is not bad, but let's add one more 0. And now something funny is happening. It's not really a curve anymore. You can see how, judging by this sort of pi, the green little pi icon, that the angle here is quite large, and here it's almost empty, it's almost 0. And then here it's large again. So it's not gradually falling off. It's sort of bending, not bending, and then bending again, not bending. But bottom line is that this is not an arc anymore. You get a straight line followed by another straight line. So before I talk about why that is and the solution to it, let's do the same thing to the joints. So I'll select this hierarchy as well, and again, go create dynamic control. So right off the bat, you'll notice that there's a much more gradual fall off here. I'm going to increase the stiffness here to the same, or I'm just going to add 1 0. So that this is now 100,000, and these boxes are at 1,000,000. And even though this is 10 times stronger, they sort of end up in a similar amount of bend. Well, so why is that? Well, let's have a closer look at this box setup. If you look real close, you can see that there's a red line here. And in fact, the connection is sort of broken. You can see how it doesn't just rotate, it also translates. And you generally don't want this red line to ever show up. This red line indicates that there's an error in the system. And the error is that, well, gravity is pulling these boxes down, the constraint is pulling it back up, but the solver isn't able to resolve that request. So the forces are they're too strong, essentially. But why would that work with the joints but not the boxes? Well, that has to do with the center of mass. So with these boxes, the center of mass on each box is in the center, and the constraint is also in the center. So what ends up happening is that gravity will pull the box down from the center, and then the constraint will try and pull it back up from the center. So they are affecting the exact same point, and yet they're still separating. So the fact that we're getting any arc, any sort of deviation from the straight line, it's an error. It's the solver is unsuccessfully solving what you ask it to do. So what really should happen here is that these boxes should just remain straight. If it manages to solve this equation, then they wouldn't bend at all. And the more stiffness that you have, the more you hide the problem, but there's still a problem. And generally, when you see a sort of break like this, you should expect some weird behavior, because the solver is struggling. This is a sign of the solver saying, I'm not able to do what you want me to do. All right, so let's tackle some solution to this problem. The first solution I'm going to touch on is to remodel your controls. So here I'm going to select the vertices of all the original boxes, and I'm just going to move them a little off center. And I'm going to try and align the edge of the box with the constraint. So now we have a center of mass over here, and the constraint is on the side. So now gravity will operate in the middle, pulling the box down. The constraint will operate on the side, pulling it up. So you'll get a rotation, a natural rotation happening. So let's see what that looks like. Okay, well, it's almost identical, right? So let's look at how to make this more accurate, because the main problem here is that ultimately the physics solver is a real, like it's trying to emulate reality. And if these boxes really were connected, they would be physically connected. They would have mass all the way, like it would fill the gap between each other. So I'm going to try and replicate that by extruding these boxes all the way to the end. So now you can imagine that if these boxes were real boxes, that they might have some sort of connection, like a physical connection, because now they are physically touching, like they're physically connected. And there we go. So already we're seeing a much better result. The solver isn't struggling anymore, because now the solver is operating with sort of realistic geometry. So now we can also reduce the stiffness to the same level. Let's bring it down to 100,000. So now the joints have 100,000 and the boxes have 100,000. And we're getting a very similar result. All right, so let's touch on another approach to solving this problem. For example, if you don't have enough geometry, like if your controllers are flat, like it's a circle or a square or something, and you weren't able to wrap around your model, your character, then the next best thing, or in fact the better thing to do, is to use these shape types. Because ultimately, the default behavior of working with controls is that it converts your NURBS controls, or in this case, polygonal geometry, into this mesh or the convex hull. And that is generally the slowest possible type of collider you can use. It's very flexible, but the flexibility comes at a performance penalty. So ideally, you would use these simpler types when you can. And in fact, just as a note, the capsule is the fastest shape that you can use. You might think it's the box because with rendering a box, it has the least amount of polygons, and a sphere and a capsule can be, well, it can be on infinite complexity. But for physics, sphere and capsules are actually the cheapest possible. So if you can get away with using a capsule, that will, well, it will save you, that will bring you the best performance. But in this case, I'm going to try and mimic the controllers and make these boxes. And I'm going to offset them in the z-axis. And so now we sort of get a double, because one is our original mesh and the other is our rigid bodies. But I'm going to try and replicate the last solution. I'm going to put them in the center, and I'm going to scale them up so that they physically touch. It doesn't have to be exact, but the more exact you are, the more exact the solver can be. There we go. So now we have rigid bodies, and they are physically connected, and the center of mass is going to be off the rotation pivot, the constraint. So again, if I bring these down in the stiffness to 100,000, we should again see the same result. All right, so the final approach I'd like to touch on to solve this problem is that if you are a bigger studio and you are separating between animation and rigging, then your first port to call is probably to have your controllers by default wrap around the model. Let's say if this was a tentacle of sorts, then if your controllers were already wrapping around the model, let's say the rig shipped like this, then when the animator then goes to make these dynamic, they would just by default work. So that is one approach. But in some cases, it might not be possible for a control to wrap around the geometry. Like maybe it's some sort of clavicle control or some special IK/FK switch or whatever. And in that case, you could provide a separate mesh, like a hidden collider mesh. And then in your pipeline, you could have a sort of a dedicated script that calls on create dynamic control. But before doing so, maybe the animator selects the control, and then your tool goes ahead and looks, is there a collider mesh related to this controller? And if so, select that first and then run the command. And then the experience will be transparent to the animator. So that's that. I hope that was useful.